Okay, students, in this video, I would like to introduce you to the individual gas laws. Now, the individual gas laws are relationships between important properties of gases. So let's first talk about what those important properties of gases there are. Some very important properties include the volume that the gas takes up, and that is with a capital V, represented volume. The pressure that we've already spoken about, the force exerted by the gas on the inner wall of a container, and that gets a capital P. The temperature of the gas, and we know that that is related to the average kinetic energy of all of the gas particles, and that is a capital T. And the number of moles of a gas, that is, how many gas particles you have. Now, we've so far used the word mole, M-O-L-E, and abbreviated it as M-O-L, but there is another abbreviation for the number of moles that is commonly used, especially in gas laws, and it's lowercase n. So let's not confuse this with the n of the energy level quantum number. Instead, this lowercase n is going to represent the number of moles of this gas. So those are four very important properties of a gas, characteristics of a gas that can be measured. And there are relationships between these properties. And there's been a lot of research going back hundreds of years to identify the relationships. And the names that are here are the common names that are associated with those laws, those relationships. So these relationships are known as scientific laws, and they are given the name of a researcher who was most associated with making the discovery, but in some cases that's a fairly controversial statement, and I'll talk more about that later. So let's start first with Gay-Lussac's law, and that's also called Amonton's law because here's a case where Gay-Lussac probably gets more credit than Amonton, but Amonton was also involved in the discovery of this relationship. And the relationship fundamentally is that pressure of a gas is proportional to temperature. So this little sign here mathematically means is proportional to. So fundamentally what this is saying is that pressure is proportional to temperature. As you increase the temperature, you proportionally increase the pressure. There's another way of writing this law, and that is that pressure divided by temperature equals some constant. So pressure divided by temperature equals some constant, and we'll just call it Q for now. And so let's unpack this a little bit. So as pressure divided by temperature equals some constant Q. And you notice that if this Q is a number, some constant, that as pressure increases, the numerator increases, then the denominator has to increase as well. So pressure and temperature, they are directly proportional to each other. As one increases, the other has to increase in order to keep this constant constant. So this constant over here is what's called a proportionality constant. And it relates how fast these two have to increase with relationship to each other. That's why we say that they are proportional to each other. Another term that we use is that they are directly proportional to each other, because as one increases, the other increases directly with it. It is a linear relationship. It's not a square relationship or a cube relationship or anything like that. So that's one relationship called the Gay-Lussac law or Amonton's law, and it relates pressure and temperature. And it can be written this way. So we might encounter it like this, or like this, or we might encounter it more commonly just as a conceptual relationship between pressure and temperature. So for example, if I were to take my empty water bottle, which is enclosed, it's got its cap on it, and this empty water bottle, we know that it has no water in it, but we know that it's also not empty. It actually has air in it, and air is a mixture of gases. So what we mean by this proportionality, as pressure and temperature are directly proportional, is that as this gas temperature increases, what does temperature mean? It is related to the average kinetic energy of all the gas particles in the sample. So as that increases, that means these gas particles are moving around a lot faster, bouncing around a lot harder, and therefore they are exerting greater force on the side of the container. So another way of thinking about this is, if I were to heat up the gas inside this bottle, then the gas would start to exert greater outward pressure or force on the bottle. Okay? So that's a relationship between pressure and temperature. Now there are 4 of these relationships that relate these important properties of a gas. And while it is important to be able to solve an equation for one of these gas laws, at this point I mainly just want you to know what the relationship is, because later I'm going to show you what's called the combined gas law. And the combined gas law will combine all of these relationships, all of these laws together, hence the term combined gas law. And if you know the combined gas law and how to manipulate that equation, then you will not need to remember and use each of these individual equations. You will be able to derive them as needed. So for now, I just want to mention these relationships, make sure you understand how these properties are related. And in this case, the pressure and the temperature are directly proportional. There is another way that we may encounter this proportionality between pressure and temperature. And that is, if we were to encounter a pressure of a gas at its initial state and the temperature of a gas at its initial state, and then compare those properties to the pressure and temperature of a gas after some change had occurred. So if the pressure divided by the temperature equals Q, a constant, and then we change something about this gas, either the temperature or the pressure or both, the Q constant will remain the same, and it will equal the final pressure over the final temperature. And what this allows us to do is we can then say P1 over T1 equals P2 over T2. Oops, T2, right? There we go. So the initial pressure divided by the initial temperature equals the final pressure of a gas divided by its final temperature. So all 3 of these represent Gay-Lussac's law, which is the fundamental relationship between pressure of a gas and temperature of a gas. And we will see this one popping up again. Let's move on. Another fundamental relationship is Boyle's Law. And Boyle's Law says that the pressure of a gas is proportional to 1 divided by the volume. So let me write that out. Pressure is 1 over the volume. Now here we have a proportionality of something where it is not directly proportional, but it is inversely proportional. And another way of saying that is that as the pressure goes up, the volume goes down. Notice that if the volume, being in the denominator here, were to increase, then the denominator gets larger and this whole term gets smaller, so the pressure gets smaller. So as the volume increases, the pressure decreases. And that's an inverse proportionality. So we can also write this as an equation relating it to a proportionality constant. So P times V, pressure times volume, equals some proportionality constant. Notice that by having these two terms multiplying each other on the same side of the equation, that indicates that they are inversely proportional. Because if S is a constant that stays the same, then as P increases, V has to decrease. Well, the way that we would see this most commonly is in a change scenario, where you have your initial pressure times your initial volume equals some constant, and that constant remains constant after the change, so then that constant also equals the final pressure of the gas times its final volume. And so there's an equation that we will see again. And when we talk about Boyle's Law, it could refer to any of these three mathematical representations, but this one here is the one we will encounter later. So let's think about what this means. Pressure and volume are inversely proportional. So let's get our sample of gas here again. Pressure and volume are inversely proportional. Well, what that means is if you increase the pressure on a gas, then its volume will decrease. So here's a simple representation of that. I'm going to increase my pressure, external pressure on this gas, and notice that the volume of the gas decreased. Okay, so that's an example of how pressure and volume are inversely related. Okay, moving on. Now we have Charles' law, or since he was French, we would pronounce it Charles' law. But I will say that Charles probably took too much credit. He probably gets too much credit for this research. Charles did publish his thoughts on the relationships between the volume and the temperature, but it was based on the work of other people. And specifically, it was based on the work of a man called Power. And Power's research was then commented on by another researcher named Townley. And so I just want to give them a shout out, and especially Power, because Power did the original research that these observations were based on. So what is this law, which we will call Charles' law, because most people are familiar with that term? Well, it relates the volume of a gas to its temperature. So the volume of a gas is proportional to its temperature. Another way of writing that is volume, and if it's proportional, then it has to be in this relationship, right? Equals some constant. And we'll call the constant U for now. So that is a constant, a proportionality constant, that relates the volume of a gas to the temperature of a gas. Notice that if U remains the same, then as the volume of a gas increases, the temperature of a gas increases. So this is a direct proportionality. As one increases, the other must increase as well. And this leads us to the more common way that we will encounter this, is the initial volume and temperature of a gas equals the final volume divided by the final temperature of a gas. And so this is a very useful relationship when we are considering the change in volume or temperature of gases. So here we have another direct proportionality. Directly proportional. Okay. All right, moving on. We have one more gas law that relates to very important properties of a gas. And this is Avogadro's law, our friend Avogadro, that we know his name really well. And so one of the relationships he discovered while he was working on his research with gases is that the volume of a gas is proportional, directly proportional to, and there's that lowercase n, that means the number of moles of a gas. So the volume of a gas, this is the number of moles of the gas, right? So the volume is proportional to the number of moles of gas. Now this shouldn't be too astounding. We would imagine that the more that you have of a gas, the more moles of gas you have, the more volume that it takes up. And so that as the moles of gas increases, we would expect the volume of a gas to increase as well. And so this is a direct proportionality again. So it must be written like this, where the volume divided by the number of moles of gas equals some proportionality constant. And the value of these proportionality constants that I've been using is not relevant to what we're doing right now, but we're about to use a proportionality constant where we do need to know the number. But so far we don't need to know the numbers for these. But here we have the volume divided by the number of moles of gas equals a constant. And you can see that as volume increases, then for the constant to remain constant, then the number of moles also increases, so they are directly proportional. And again, the more common way that we will encounter this relationship is when we have a change of gas properties. So the initial volume divided by the initial number of moles of gas equals the final volume of the gas divided by the final number of moles of the gas. So again, any of these mathematical representations are valid representations of Avogadro's law, but this is the one that we will encounter probably most for our purposes. Now, just a quick review of these. I want to point out, again, that there are some fundamental relationships here. As you increase the temperature on a gas, its pressure will increase. Next, pressure and volume. They are inversely proportional. So as one increases, the other decreases. So if I were to increase pressure on a gas, then its volume would decrease. Ch8 law, or the Power-Townley law, volume and temperature of a gas are directly proportional. As one increases, the other increases. And I've mentioned in a previous video that a classic example of this is the hot air balloon. That as we increase the temperature of the gas, the air gas inside the hot air balloon, then the volume of the gas inside the hot air balloon also increases. And because the volume of the gas increases, it is less dense than the air outside the balloon, and so the air inside the balloon will float on the air outside the balloon. And that's the principle of why a hot air balloon will work. So volume and temperature are directly proportional. As one increases, the other increases as well. And then finally, a fairly straightforward statement here, Avogadro's law. As you increase the number of moles of gas, then you're increasing the volume. It just takes up more space. Okay? So these are fundamental relationships called the individual gas laws because they relate the individual properties of a gas to each other. I want you to understand the fundamental relationships with them, but you are not going to have to memorize these equations because here in a bit we're going to cover the combined gas law, and the combined gas law will have all of these equations wrapped up in it. And if you know the combined gas law, and how and when to manipulate it, you will be able to generate each of these equations as you need them.